So this is just an overview of the course. We'll start with an introduction saying where complex numbers come from. Complex numbers basically complete the numbers. If you take a complex number to a power of a complex number, you still get a complex number, for example. So they're nothing particularly strange. They're the missing piece of all the numbers. So then we go on to basic properties. If you've studied complex numbers before, then this will just be revision. Now, this course, after we get through the basic properties, will seem like nothing you've studied before. It will seem almost magic, because what we'll end up doing is finding definite integrals without doing any integration. So normally when you find, say, this definite integral, you would recognize this as, well, the antiderivative of 1 over a squared plus x squared is inverse tan, and then you substitute in these limits into inverse tan. But the techniques we're going to learn mean that you don't need to know the antiderivative of this, and it will seem like magic. Just to give you a taste without explaining what I'm doing, to get the answer to this, you'd end up multiplying 2 pi I by, you actually differentiate this bit on the bottom to get 2x, and then inside the 2x, you actually substitute where this function here on the bottom is 0. So you end up with, well, it's going to be 0 when x is I times a. So differentiating the x, you get 2x, so it's 2i times a, and you get the answer pi over a. So this seems very mysterious at the moment, but all will become clearer later in the course. Now, of course, this is a fairly straightforward integral to do using ordinary techniques. But if I modify it now and change the top to something like cos 2x, for example, now this becomes much more difficult using ordinary techniques. It's not obvious what the antiderivative of this is, but using the techniques we're going to study in this course, it's actually not much more difficult. I will just write down what you end up doing. You end up writing the cos 2x as e to the I 2x, and do the same sort of substitution as before. So we'll end up with a 2 times the IA, and the bottom bit stays the same as before. We end up with a 2IA on the bottom, and we multiply by 2 pi I. So the final answer then is e to the minus 2a pi over a. Again, this seems rather magic. You can do integrals like this very quickly. How this all works will become clear later on in the course. Similarly, with sums, you might possibly know what the sum of 1 over n squared is. How do you prove that? Well, you might have possibly proved it using tricks using Fourier series, but so far you probably don't know a general method of getting sums like this, but this complex analysis will teach you such a general method. We'll also, if you've studied forward Laplace transforms, you might have possibly studied that. The inverse Laplace transform is rather a strange looking integral, looking something like c minus I infinity, c plus I infinity of the Laplace transform you're trying to solve. So we'll explain what this means and how to get the Laplace transform, inverse Laplace transform. And the final thing we'll look at is something called conformal mapping. Conformal mapping basically allows you to, for two-dimensional systems, find the potential distribution of interesting looking shapes. So for example, if I were to say that I've got this step here, and all of this step is at a certain potential, then I want to find, as a function of x and y, what the potential is at a certain point here. What is the potential Vxy, if say I know the potentials along these lines here. This would normally be a very difficult problem to solve. Or another example would be, say I've got a cylindrical conductor like this, and I've got another cylindrical conductor, but they're not aligned. Okay, so what's the potential in this region here? There's there's very little symmetry. It's not circularly symmetric. So again, conformal mapping allows you to solve problems like this. You could, for example, find the capacitance of this system. Obviously, it's very easy if this is in the center, but if it's not in the center, you can actually also use this technique to find the capacitance per unit length of a conductor like that.